history doesn't just lie beneath our feet, it has been actively trying to teach us how to build our future. Welcome to the frontier where lost ancient engineering meets cutting-edge modern design. For decades, we assumed our ancestors were primitive builders scratching a living out of the dirt. But as advanced technologies like LiDAR strip away centuries of jungle canopy and modern climate crises force us to rethink how we live, a stunning reality is coming to light. Ancient civilizations solved the very problems we are facing today. From zero-energy cooling towers in ancient Persia to self-sustaining urban grids in the Amazon and earthquake-proof megaliths that defy modern physics, the blueprint for tomorrow isn't waiting in a high-tech lab, it's buried in our past. If you want to build the future, you have to look backward. What if the future of architecture isn't something we need to invent? What if it's something we've forgotten? For more than a century, humanity has built upward. Steel, concrete, glass, air conditioning. Millions of buildings designed to protect us from the natural environment. But there's a problem. The buildings we created to make modern life more comfortable have also become enormous consumers of energy and resources. And as cities become hotter, weather becomes more unpredictable, and environmental standards become stricter, architects are facing a completely new question. Can buildings become part of nature instead of simply standing against it? Across the world, researchers and architects are looking for answers in an unexpected place. Not just in advanced technology, but in biology. And not only in biology. They're also looking backward, toward ancient structures that survived centuries of heat, earthquakes, flooding, and environmental change. The result is a fascinating architectural philosophy. Biomimetic architecture. And its most ambitious form may be something even more radical. Living architecture. The building that breathes. Imagine a building that can regulate its environment without depending entirely on mechanical cooling. It sounds futuristic, but nature has been doing it for millions of years. Termite colonies build complex structures containing chambers, tunnels, and ventilation pathways. These structures help regulate the environment inside the colony. Warm air moves. Cooler air enters. Heat is redistributed. The colony and its environment work together. Architects began asking a simple question. What if buildings could learn from this? That question helped inspire one of the world's best-known examples of biomimetic architecture. The Eastgate Center in Harare, Zimbabwe. Its design incorporated passive ventilation and thermal mass principles inspired partly by termite mound behavior. The goal was to copy a termite mound literally. It was to understand the strategy behind it. Nature doesn't waste energy fighting its environment. It adapts to it. And that idea sits at the heart of biomimicry. What is biomimicry? Biomimicry means learning from nature. Not simply copying what nature looks like, but studying how nature solves problems. A leaf captures sunlight. A building can learn from that. A termite colony regulates temperature. A building can learn from that. A tree distributes forces through branching structures. Engineers can study that. A shell achieves impressive strength using relatively little material. Structural designers can learn from it. The question changes from, how can we build a stronger machine? To, how has nature already solved this problem? That small change in thinking can completely transform architecture. The ancient blueprint. But biomimicry isn't entirely new. In fact, some of its most interesting lessons come from ancient architecture. Consider ancient Rome. The Pantheon has survived for nearly 2,000 years. Its massive dome remains one of the great achievements of ancient engineering. Roman builders also developed concrete mixtures that behaved differently from many modern concrete systems. Researchers studying Roman concrete have found evidence of unusual chemical processes that may have contributed to its remarkable durability. But the real lesson isn't simply that ancient concrete was better. The deeper lesson is that ancient builders understood relationships. They understood materials. They understood climate. They understood water. They understood gravity. And they understood time. Modern architecture often tries to control environmental forces. Ancient architecture frequently worked with them. The architecture of shade. Travel thousands of kilometers east, and another principle appears. In traditional Middle Eastern architecture, screens known as mashrabiya provided shade, privacy, and opportunities for airflow. They weren't simply decorative. They helped control the relationship between sunlight, air, and interior space. Instead of allowing intense sunlight to enter directly, the facade filtered it. The building became a climate control system. And today, architects are rediscovering this idea through responsive facades, external shading systems, perforated screens, and dynamic building envelopes. Technology has changed, but the principle remains. A wall doesn't have to be a barrier. It can be a filter. Learning from water. Then there's water. Modern cities often treat rainfall as something to remove as quickly as possible. Rain falls. It enters drainage systems. And it disappears. Ancient civilizations often approached water differently. At Angkor, the Khmer civilization developed enormous systems of reservoirs, canals, and waterways. Water wasn't simply outside the city. It was part of the city's infrastructure. The lesson for modern architecture is powerful. Instead of asking, how do we get rid of water? We can ask, how do we capture it, store it, filter it, and reuse it? That principle is becoming increasingly important as cities deal with heavier rainfall, drought, and water stress. The building of the future may not simply have a roof. It may have a complete water ecosystem built into it. Buildings that move. Some ancient structures understood another force remarkably well. Movement. Traditional Chinese timber architecture used sophisticated interlocking joints that allowed structures to flex and distribute forces. This principle is particularly relevant when thinking about earthquakes. Because during an earthquake, absolute rigidity isn't necessarily the goal. Sometimes controlled movement can be safer. Modern seismic engineering uses advanced materials, dampers, flexible connections, and sophisticated structural systems. The technology is different, but the principle is familiar. Strength doesn't always mean refusing to move. Sometimes strength means knowing how to move. From sustainable to living. Traditional sustainable architecture focuses on reducing harm. Use less energy. Produce less waste. Lower emissions. Reduce environmental impact. These goals are important. But living architecture asks a more ambitious question. What if a building could actively contribute to its environment? Imagine walls covered with vegetation. Roofs that capture rainwater. Facades that provide habitat. Materials designed for reuse. Surfaces that reduce heat. Structures designed to adapt instead of simply deteriorating. The building stops behaving like a sealed object. It becomes part of an ecosystem. The living facade. Living facades are one of the most visible examples. Plants can provide shade. Through evapotranspiration, vegetation can influence surface temperatures and local microclimates. Green systems can also provide habitat and help manage stormwater. But there's an important reality check. A green wall isn't automatically sustainable. Plants need water. Plants need nutrients. Plants need maintenance. And the wrong species in the wrong environment can create additional problems. That's why genuine biomimetic architecture isn't simply about adding plants to a building. It's about designing the entire system around ecological principles, the mycelium revolution. Deep beneath the surface of forests exists one of nature's most fascinating networks. Mycelium, the thread-like network that forms the body of many fungi. It connects ecosystems, breaks down organic material, moves nutrients, and creates incredibly complex biological networks. Researchers are investigating mycelium-based materials for insulation, panels, packaging, and other applications. Imagine materials that can grow. Materials created through biological processes. Materials that could potentially return to natural cycles at the end of their useful life. It sounds like science fiction, but research is already underway. The challenge is transforming these promising biological concepts into safe, durable, scalable building materials. The economic question. For architects, the environmental argument is powerful. But developers and investors ask another question. Does it make financial sense? And that's where biomimetic architecture becomes especially interesting. The cost of a building isn't just its construction price. There are decades of energy bills, maintenance, repairs, renovations, regulatory requirements, insurance, tenant demand, and eventually resale value. A building that costs more initially but significantly reduces operating costs can potentially become economically attractive. But there's no universal guarantee. Climate matters. Energy prices matter. Building type matters. Maintenance matters. And a biomimetic label by itself doesn't create financial value. The design has to perform. The first mover advantage. For major real estate markets, another factor is becoming increasingly important. Differentiation. Thousands of buildings compete for the same tenants and investors. A building with exceptional environmental performance can become more than real estate. It can become a landmark, a brand, a demonstration of technological leadership, and potentially a valuable long-term asset. But the most successful buildings won't necessarily be the ones with the most technology. They'll be the ones where the technology becomes almost invisible, where the building simply works. Like a forest, like a termite mound, like a tree. One planet mini-climates. There is no universal biomimetic building. Nature doesn't work that way. A polar ecosystem is different from a desert. A rainforest is different from a Mediterranean landscape. Architecture must respond to local conditions. In cold climates, thermal storage and solar gain can be critical. In temperate climates, humidity and natural ventilation become important. In hot, dry regions, shade, thermal mass, and evaporative cooling can play major roles. And in hot, humid environments, airflow and moisture management become essential. The principle is simple. Study the local ecosystem. Ask what has survived there. How does it handle heat? How does it manage water? How does it capture energy? How does it protect itself? Then ask one final question. What can architecture learn from it? The maintenance problem. Of course, living architecture has challenges. Complexity is one of them. A conventional building can be mechanically complicated. A living building can be biologically complicated. Plants grow. Water moves. Materials age. Ecosystems change. Biological systems don't always behave exactly as predicted. So the future isn't about eliminating maintenance. It's about making maintenance smarter. Sensors can monitor moisture. Building management systems can track energy. Automated irrigation can respond to environmental conditions. Digital models can predict performance. Biological systems can work alongside mechanical systems. The goal isn't to replace technology with nature. It's to combine them. The 100-year building. Now imagine something different. A building designed not for 30 years. Not for 50 years. But for 100 years or more. A structure where components can be replaced independently. A facade that can adapt. A water system that becomes more efficient. A landscape that matures. Materials that can be disassembled instead of demolished. Architecture that becomes more valuable because it gets older. That changes the definition of sustainability. Instead of asking, how do we make buildings consume less? We ask, how do we make buildings last longer, adapt better, and give more back? The future of architecture. The architecture of the future may not look like a forest. It may not look like a termite mound. And it certainly won't look exactly like an ancient ruin. Instead, it will borrow the principles behind them. Efficiency, adaptation, resilience, regeneration, integration. Ancient builders understood something modern civilization sometimes forgets. A building doesn't exist alone. It exists inside a climate, inside a water cycle, inside an ecosystem, inside time. The most advanced architecture may therefore be architecture that understands its limits. Architecture that doesn't attempt to dominate nature, but learns from it. For thousands of years, humanity has asked, how can we build higher? Then, How can we build faster? Then, how can we build cheaper? Perhaps the next question should be different. How can we build better? Not just for the next decade, but for the next century. Not just for the people inside the building, but for everything around it. Because the greatest building of the future may not be the one that conquers nature. It may be the one that behaves more like nature. A building that breathes. A building that adapts. A building that captures. A building that regenerates. A building that ages without becoming obsolete. And perhaps after thousands of years of architectural experimentation, we're finally beginning to understand something nature knew all along. The most resilient systems don't fight their environment. They become part of it. If you enjoyed this journey into the future of architecture, don't stop here. Subscribe to the channel for more documentaries exploring future technology, ancient engineering, sustainable design, and the ideas that could reshape civilization. And if you believe the buildings of tomorrow should work with nature instead of against it, share this video with someone who cares about the future of our cities. The future of architecture may already be hiding in the past. The question is whether we're ready to learn from it.